Well, we continue our morning session, and it's my pleasure to introduce the next speaker, Atsuki Kuramoto, and he will speak about the density of Borromean primes. So may I ask you to share your screen?
Thank you for your introduction, and I would like to thank the organizers for giving me the opportunity to speak at AGMA. The title is The Density of Borromean Primes. This research is joint work with Yuki Ishida and Dinchen Zhang. This presentation consists of the showing contents. First, I talk about analogies between number theory and three-dimensional topology and classical density theorems. Subsequently, I explain the assertion and proof of our main theorem. Finally, further studies will be presented. First, I will overview arithmetic topology. Arithmetic topology is a field that promotes mutual development based on analogs, number theory, and three-dimensional topology. Arithmetic topology is created by Mary Mazer, Masanori Morishita, Mikhail Kaplanov, and Alexander Reznikov. Various analogies between number theory and three-dimensional topology have been found so far. Those analogies have been listed as a dictionary called M2KR dictionary. For example, integer rings of number fields correspond to three-dimensional manifolds. This correspondence arose as prime ideas as knots. According to this view, finite set of prime ideas are linked. Furthermore, the Legendre symbol in number theory is the analog of Gauss-Motte linking number in three-dimensional topology. In other words, Legendre symbol describes how linked two primes are. When the Legendre symbol is 1, those primes are not linked. On the other hand, when the Legendre symbol is -1, those primes are linked. For example, 29 is quadratic residue modulo 5, so 5 and 29 are not linked. By construct, since 13 is not quadratic residue modulo 5, 5 and 13 is linked. In addition, 4 primes congruent to 1 modulo 4, the Legendre symbol is symmetric by Gauss reciprocity law. This is analogous to the symmetry of linking numbers. Next, let me tell you the Ledai symbol. The Ledai symbol can be regarded as a triple generalization of the Legendre symbol. According to arithmetic topology, the Ledai symbol corresponds to the Mott-Milner triple linking number. In order to explain the Ledai symbol, I talk about the tower of field extension in this picture. Okay, let P1, P2 be prime numbers congruent to 1 modulo 4 and quadratic residue modulo the other. Then, we can construct a dihedral extension K of Q with order 8. This field K is called Ledai's extension. The Ledai symbol is defined by using this field K. Let P3 be prime congruent to 1 modulo 4 and quadratic residue both P1 and P2. Then, the Ledai symbol tells us how P3 splits in the field K. In other words, if P3 is completely decomposed in K, the Ledai symbol is 1. And otherwise, the symbol is -1. This definition is a natural generalization for the Legendre symbol. Recall that the Ledai symbols is arithmetic analogs of Mott-Milner's triple linking number. That is, when the Ledai symbol is 1, then the triple primes are not linked. But when the symbol is -1, then triple primes are linked. According to this view, Borromean primes can be defined as shown in this slide, introduced by Morishita. The conditions about the Legendre symbol mean that any two of the primes are not linked. And the conditions about the Ledai symbol means that all of them are entirely linked. Those linking conditions are same as Borromean links in topology, which is the origin of the name Borromean primes. These are examples of Borromean primes. We can confirm that those examples satisfy the conditions of Borromean primes. I will focus on the tuple 13, 17, 53. In Ledai's extension K obtained from 13 and 17 is top of the right tower in this slide. This picture shows that 53 is decomposed into 4 distinct prime ideas in this K. Therefore, the Ledai symbol 13, 17, 53 is -1. Next, these are examples of not Borromean primes. For example, the triple 5, 29, 149 corresponds to a trivial link in which none of them are linked. The tuple 5, 13, 29 corresponds to a link like a chain. I talk about 5, 29, 149. This picture shows that 149 is decomposed into 8 distinct prime ideas in K. Therefore, the Redai symbol 5, 29, 149 is 1. Next, we introduce classical density theorem in number theory. The upper theorem, called the prime number theorem, was conjectured by Gauss and proved independently by de Laval-Poussin and AGMA. And generalization of this theorem is known as Dirichlet's theorem on arithmetic progressions. Also, not mentioned here, these can be generalized as Chebotarev's density theorem. Now, I talk about our main theorem. This theorem shows that the density of Borromean primes among all the triples of primes is 1 over 128. You may think this main theorem is derived from only classical density theorems, but it is necessary for the proof the elaborate analysis of the error term of Chebotarev's density theorems. In order to analyze the error term, we employed this theorem. Some of you may think why generalized Riemann hypothesis is necessary for the proof. In fact, it is needed to obtain this theorem. In addition, the discriminant of Redai's extensions is necessary for using this theorem. So we calculated the value explicitly with some formula of discriminants. Further questions is to calculate the density of primes satisfying the higher order linking conditions. According to arithmetic topology, the analogy between the Redai symbol and Mott-Milner triple linking number is generalized to the analogy between the multiple quadratic residue symbol and the Mott-Milner's linking number. As Redai symbol and Mott-Milner linking number, those generalizations are the analog of the other. The Mott-Milner linking number describes how linked several nodes are. So because of that analogy, we can derive the idea that several primes are linked and think the density of such linked prime. However, Little is currently known about the generalizations of the Ledai symbol. I will obtain more concrete properties of the multiple quadratic residue symbol and apply that result to calculating the density of primes, satisfying the conditions written in the symbol. Our paper has been accepted for this journal and will be published. The paper is available on arXiv. Thank you very much for your attention.
Thank you for your interesting talk.